Okay, this is problem 14103. It's on page 643. There's a figure there to go with it, so you'll want to reference the figure. I'll read it. Water flows in a continuous sheet from between two plates A and B with a velocity V of magnitude 80 feet per second. The stream is split into two parts by a smooth horizontal plate C. Determine the rates of flow Q1 and Q2 in each of the two resulting streams, knowing that the angle theta is 30 degrees and that the total force exerted by the streams on the plate is 75 pounds of vertical force. Now they've given us a density for the water that says that, or well, not a density, excuse me, it's a conversion factor. It says 1 cubic foot is 7.48 gallons. So I'll begin by sketching the problem again. Of course, this is 14103. And there's two plates. The purpose of the plates is simply to force the water to flow in a predefined manner. We draw the plate down here that it's hitting. And we were told that there are 17 pounds force that the plate applies. Excuse me, 75 pounds force that the plate applies to the water stream. So somehow that plate would have to be supported, or what I've tried to draw here is just the force that the plate would apply to the water stream. Now the water stream goes like this. It comes down, and then as it hits the plate, it turns and flows like this. Now the height of flow will in fact be different. It turns out that in theory, if the stream were coming down vertically, the height of flow on either side would be equal. But there's one piece of information that was given that was very important. And it's not real obvious, and that is that the velocity coming in and the velocity leaving are the same. That doesn't mean the volumetric flow rate is the same. Okay, now imagining this would just be extruded out, whatever width we want it to be extruded out. Okay, so we're far enough from the ends so that this is the average behavior over this entire cross-section extruded from the board. Okay, this is not a round stream, this is just a flat stream. Okay, now the velocity of flow in and out would be the same everywhere. There's a reason for that. You can derive that from Bernoulli's equation. Bernoulli's equation is not part of this class, so we won't go through that part. It's just given that those are the velocities. Now, what's a little bit tricky about this is that we have a single entrance, A, but we have two exits, B. Not just a single exit. Okay, so how do we deal with that? Well, I'll show you how to deal with it. In fact, let me call this B2 and B1.
I thought the plate is for plate A, plate B.
The plate is right here.
How about this plate over there?
A and B, yeah, they give us those names, but because in the equation we have sum of forces equals mass flow rate VB less VA, and I want to use that equation.
Okay.
I'm going to let B and A refer to the entrance and exit rather than the plates. We can call it plate 1, plate 2 if you want. It doesn't really matter. They're just there to force the stream to do this. Another bit of information, the velocity of flow coming in and leaving, of course, that velocity V is 80 feet per second. And that's the same whether we're talking about the entrance or the exit. Of course, it's obvious that the direction of flow is different. And that's the key difference. Another piece of information, the stream comes in at an angle to vertical of 30 degrees. Okay? I'm going to attach a coordinate system that looks like this. X to the right, Y positive up, because I have to be careful with the directions in using this equation. So let's start with this equation and see what we can do with it. So first of all, since it's easiest, let's sum forces in the Y direction. Right? That way we don't have to deal with the X direction yet, which is going to be a little trickier. Summing forces in the Y direction would have the mass flow rate multiplied by the velocity at B in the Y direction less the velocity at A in the Y direction. We have two different B's, but both of them have zero velocity in the Y direction, so we get to cross that off and not worry about it too much. Okay. Now, the mass flow rate Trying to remember why I put a negative sign on this. Oh, I know why. Yeah, okay, let's do it this way. So this is equal to the mass flow rate. We need the negative of the velocity at A in the y direction. But notice that the velocity at A in the y direction, the component that we need right here, is actually a negative thing. So VAY is a negative, correct? So if we calculate VAY, how would we do it? Well, we just need the component of V, right? We need V. Would it be times cosine or sine of 30 degrees? Cosine, that's right, because the angle's right here, and we want the piece that's touching the angle. Make sense? So we need cosine of the angle. So let's see, if we do that, I didn't do that in by itself, I did it in context, but let's go ahead and calculate it just because it's here and it'll keep you busy. So 80 feet per second, cosine 30 degrees. Let me move my coordinate system a little bit. Get it out of the way. So plug that in your calculators, please. And let's see what the velocity in the y direction. Now, I've already made a mistake, right? It should be negative right here because I know it's down. So I need to get a negative out of this. So 80 times cosine 30 is how much?
69.28.
69.28, and that's a negative, and feet per second. Okay, so now we've got VAY. And we can just plug it in, except notice we don't have the mass flow rate yet. So how will we get the mass flow rate? Well, let's see. The mass flow rate, let's see, let's do it down here. The mass flow rate coming in at A would be equal to the density of the water multiplied by the volumetric flow rate. Now, the density of the water times the volumetric flow rate could be written in terms of the velocity as the cross-sectional area at A times the velocity at A. Of course, the velocity is the same everywhere, so I won't put an A subscript on it. Do you guys understand this? If I know the cross-sectional area at A and I multiply that by the velocity, I will get volume flow rate. Okay? Does that make sense to everybody? I see blank looks.
Yeah, again. Yeah.
If I multiply the velocity of flow by the cross-sectional flow, I'll get the volumetric flow rate. Okay? Hopefully you've seen that before in other courses. All right? So basically what I need here is, let's see, density, area at A, velocity multiplied by velocity at A in the y direction. Do you see the difference between these two? This is the total velocity. This is the velocity that we computed the component. All right? And density would just be the density of water, which we can look up, or they may have given it to us, I don't recall. And we need the cross-sectional area at A. Now, let's see. What did they ask us to find? I'm getting lost here. Let's find out. I should have written that down, thanks. It's Q1 and Q2. So we need to know the flow rates. They've called this 1 over here. I apologize, I use the opposite, so let me switch that. 1, 2. They want to know Q1 and Q2, where those two are just the volumetric flow rates. Now, they're using Q instead of V dot, so I could do the same. Right? Notice that Q1 and Q2 added together would be Q, because the flow rate Q here is just the velocity times cross-sectional area. This would also be the velocity times the cross-sectional area at B1. This would be the velocity times the cross-sectional area at B2. Okay? I guess I could just use a 1 here, since really they've made this cross-section 1 and this cross-section 2. Doesn't matter, it's just what we want to call it. Okay? All right,
Should that be the Q1 equal B1?
It's the cross-sectional area at section 1. So the cross-sectional area at A1 would be right here. So this would be A1. It's extruded out however far.
Okay.
And just like this would be A2. Okay. All right. Now I should have everything we need. Okay, anybody know the density of water right off? Have that memorized? It's 62.4 pound mass per cubic foot. That's one of the numbers that's worth committing to memory. Of course, this is at standard temperature. The density of water varies a little bit, not a whole lot. Now, do you notice that really the only unknown is the cross-sectional area A? Because we know the force in the y direction that acts on the water is 75 pounds. So what we could do, let's separate that out, what we could do is say, well, the area at A can be computed as sum of force in the y direction divided by density times velocity of flow times V A Y. And really, I still need a negative sign in here because VAY is negative. Okay. Now, if you're doing this on the video, I would suggest you try to get this result. And those of you in class, you may want to try as well. You'll have to use G sub C as a conversion factor in this. But you should get an area of about 6.9827 times 10 to the negative third square feet as the cross-sectional area at A. Okay.
So what the velocity would be 80 feet per second,
This is
right?
80, right?
Okay.
This is negative 69.28.
Okay.
This is 62.4. This is 75 pounds force, and the units won't match, so you have to throw G sub C in there to get it to come out. Because notice you'll have pounds mass in this and pounds force here. Okay, good question. Any others so far? So we've got the cross-sectional area at A, and really we could get Q at this point. So let's see, I must have done that here somewhere. I didn't bother with it. But if you wanted to, you could simply multiply the velocity times this area we just found and get Q. You'll notice that that actually appears in the equation right here. So this really is just Q, the volumetric flow rate. And I wrote Q dot, I'm sorry, that's a thermo habit. So far so good? Well, what can we do with it now? Let's see. Now, all of the mass that comes in here in 1 second must come out here and here, right? It has to split up, and some of it goes this way, some of it goes this way. That means that the mass flow rate at A equals the mass flow rate at B1 plus the mass flow rate at B2, right? Because it just splits up and goes two separate ways. This is a mass balance, and once you get to 220, we'll use these quite a bit, but you can see intuitively how this works. Now, we could expand this a little bit and write it in terms of density and volumetric flow rate, but we could write volumetric flow rate in terms of cross-sectional areas times velocity. So this would be VAA equals rho V multiplied by A1 plus rho V A2, right? But it's obvious that the density of the water at all the cross sections is the same, and we were given that the velocity of the water at all the cross sections is the same. Therefore, the cross-sectional area at A must be equal to the sum of the cross-sectional areas at 1 and 2, and you can see my drawing's way out of scale now, right? Because this distance plus this distance should be this distance, since we have the same width. Yes?
For your cross-sectional area,
Yeah, right here.
yeah, I'm not getting that number.
Well, let's find out. It was, let me get rid of some of this. In fact, let me move this out of the way. Can you see where that came from? The area at A is A1 plus A2. That way that's out of our way. Now the equation was sum of forces in the y direction, so that's 75 pounds force. We had a negative sign. The density of the water, 62.4 pound mass per cubic foot. The velocity, 80 feet per second. And then the velocity at A in the y direction is negative 69.28 feet per second. Did you remember G sub C? There should be 32.2 pound mass feet per second squared per each pound force, otherwise it won't come out. The units wouldn't come out at all. Let's see what else cancels. We'd have, and by the way, this was the cross-sectional area at A. We should end up with feet squared. Yeah, the seconds are gone. And so we've got feet to the fifth in the denominator. No, we don't. We've got feet squared over feet cubed, so 1 over feet. Yeah, so this foot will go in the numerator, so we will have square feet, so that's okay. Now what number do we get here? You guys plug this in your calculator.
You got the right answer.
The two negatives will cancel. So this is okay after all?
It
Okay.
is. I just forgot
Forgot G sub C? Okay, it's easy to do, no problem. Thank you for checking. Okay, but do you guys understand why the cross-sectional area at A must be equal to the sum of the cross-sectional area of 1 and 2?
Yes.
Because the mass flow rate mass has to be conserved essentially. Okay, well, we played around with the y direction and got about as much information as we can. So let me just make a note over here that this is 6.9827 times 10 to the negative third square feet. And then we should have space then to do what we need to do. Okay. What are we going to do in the x direction? We need to sum forces in the x direction. Well, actually, it's pretty easy. Notice that each of the terms is a mass flow rate times a velocity. So all you do is you add one more term. The mass flow rate at section B1 multiplied by the velocity at B1, because notice this is an exit, right? And so our equation is sum of forces equals mass flow rate, VB less VA. Since we're riding in the x direction, then we need the mass flow rate at the various sections. Before that wasn't a question. There was one entrance, one exit, and therefore the mass flow rate at the entrance and exit was equal, so it wasn't a problem. Well, what we need to do now, since we have two exits, is we have to have one term that represents one exit and another term that represents the other. Now, the other term will look like this. It'll be plus the mass flow rate at B2 times the velocity at B2, right? But then we have to subtract off, because we've got a negative sign, the mass flow rate coming in, which is the total mass flow rate, times the velocity at A. And notice these are all in the x direction, but I'm going to make it explicit for A because A has both an x and a y component. Okay? Now we have to be even more careful in this because we're talking about momentum. And notice that since A is coming in, although it has a positive x component, it will give us a negative, looks like momentum term. It's not really, but almost a momentum term, right? That's what it gives us, is a negative contribution to the equation. Notice that this term, which is in the negative direction, will have to give us, we'll have to plug in a negative sign for this velocity, right?
Yes.
And we'll have to plug in the positive sign for this one. Now I'm looking at my sheet, and I'm afraid I may have done this wrong in my solution. But let me think for a second to make sure that I've done this right, because let's see, VB, if it's positive, should end up positive. But B1 is, oh, I know what's wrong. Remember I switched the order? I had B2 here and B1 here. So that's why in my solution I've got them written out of order. Okay, this will work out just fine.
But B1 should be negative, right?
B1 will be negative,
Okay.
yes. The velocity at B1 will be negative. In my solution I was calling that 2, and that's why I put a negative sign in front of it. Okay. So if you're looking at this sheet, I'm sorry that it's confusing. I called this side 2 and this side 1. I forgot what the authors had done. But we'll go through, and rather than following my solution that I made, we'll just plug it in, and then we'll check and make sure we have arrived at the same point, which we should. Okay, so the mass flow rate at B1, well, we could write that as density at B1 multiplied by, and here's where we'll have to be really careful about the signs, okay? We need the density times the cross-sectional area at B1 times the velocity at B1. But what I've got here is the volume flow rate times density. And I need a positive thing, but VB1 is going to be negative, so I've got to stick a negative sign on it. Does that make sense? Do you see why I have to do that? I'm just trying to get a positive mass flow rate here, but when I plug in VB1, I'm going to plug it in negative, because it really is a negative thing. Okay, and this VB1 comes from here. You guys understand why I had to put that on? Another way we could do this is I just need the absolute value of VB1, because I'm trying to get a mass flow rate. So if you want to think about it that way, that's fine too. Now, the next term, VB, or the mass flow rate at B2, I need to do the same thing. I need the density multiplied by the cross-sectional area at B2 times the velocity at B2, and this bit here is just the mass flow rate at B2. But then I have to bring this term down and multiply by VB2. Here I don't have to worry like I did here because all of it's positive. So that should come out fine. It should give me a positive momentum. Now I've got to break the line for the sake of the video, so minus mass flow rate. This is all the mass flow rate at A. So to write it, I'd write it density times cross-sectional area at A times the total velocity.
Why that's not negative again?
This one?
Yeah,
Because I put absolute value signs around the VB1.
okay.
This VB1 will be negative. This one is too, but I've taken the absolute value, so I get a mass flow rate. Good question. Any others so far? Now notice that, let me finish off this term. This is just the mass flow rate at A, and I need to multiply it by the velocity at A in the x direction. Now understand, I'm not concerned about the direction of this velocity. I know it's got a negative y component, positive x component. Once again, I'm just trying to calculate the mass flow rate. That's all I'm trying to do. And this negative sign just comes from there. Are we doing okay so far? All right. So, now notice something interesting here. Notice that the area at A here and the area at B1 and the area at B2, the area at B1 plus the area at B2 is equal to the area at A, right? We already know that. Notice the densities are all the same. So what could we do with this? Well, let's see. Bless you. Okay. How much force is there in the x direction? Is there any? There's none, right? Now, I know your intuition's probably kicking and screaming because you say, well, wait a second, there's going to be friction with the plate against the water. You're right, but we're not talking about that part. That's going to be a small amount. It's not going to change the momentum of the stream as much at all. Okay? So we're going to neglect the force in the x direction and say this sum of forces in the x direction is simply 0. If we did that, we'd get to cross off all of these densities because they are all the same, right? Okay, so then what? Well, let's clean it up a little bit. Let's write it again. I'm going to move this out of the way so that we can have some space. So this is Q2 equals A2 multiplied by V. Okay, so that way, hopefully it's not too bad. Okay, so let's rewrite this. Basically, 0 equals the area B1. Let's just put the negative sign on it so I don't have to deal with the absolute values. VB1, and really it's squared now, plus, this term will give me AB2, VB2 squared, and then this term will give me minus area at A, V. Now I'd like to write this squared if I could, and one way to do that would be to say, well, the velocity can be written, let's see, well, we haven't written it yet, right? Let's take care of VAX first. We've use this, we don't need it anymore. So let's compute the x component of the velocity, VAX. I should have made that bigger, let's pull it out. VAX is what? We're gonna use sine or cosine to get this? Well, we use cosine to get this component, right? So we're going to use sine, not because it's in the horizontal direction, but because the angle touches the vertical side. So if we want this side, the angle's kind of like shining on or looking at the other side. So we have to use V multiplied by sine of the angle. So far, so good? So, let's see. So let me get rid of VAX in lieu of V. So that way I'd have V squared here, right? Because I'm going to take V times VAX, but AX is just this. So that'll give me a V squared sine theta, right? Now, is the velocity at B1 and B2 different or the same? We were given that they were the same, right? So the velocity at B1, the velocity at B2, and the velocity at V, these are all the same, and so the square of them will also cross off. Okay. Now what? Well, 0 equals negative area at B1 plus area at B2 less area at A times sine theta. Okay. So what are we doing here? Well, notice that we've got one equation that relates A1 and A2. We're going to end up with an independent equation that relates A1 and A2. Because I'm sorry, I'm not being as careful with the symbols as I should be, but the area at B1 is the same thing as the area at 1, and the area at B2 is just the same thing as the area at 2, right? So I guess at this point, to make things simpler, I'm just going to get rid of the B. So we can just talk about the area of section 1 and the area of section 2. These two are two separate independent equations for A1 and A2. Notice we already know the area at A. We know the angle theta, so we should be able to solve for A1 and A2. Why would I need that? Because we were asked to find Q. And as soon as we get A1 and A2, we will have Q1 and Q2. Right? What have I used? Well, this really came from a conservation of mass equation, whereas this is a conservation of momentum equation. It's pretty common that you have to use conservation of mass and conservation of momentum to solve problems like these. So I think we are done with this bit. Let's solve for A1 and A2. Let's see, have you guys had linear algebra yet? Okay, well, we'll do it the long way. A1 from the mass balance is area at A less area at 2. Everybody see that all I've done is rearrange this equation, right? So if I plug that in to the momentum balance, then what I would have is 0 equals negative A1, but A1 is area at A less A2, okay, plus A2, okay, less the area at A sine theta. Now I'd like to get A2 by itself. Notice negative of negative A2 is positive. So I'd have A2 plus A2, which is 2A2. I'll move that to the other side and have negative 2A2 equals negative AA minus AA sine theta. Did everybody follow that? You okay still? All I did is I realized this is positive A2 plus this A2 is 2A2. Move to the other side is negative 2A2. That takes care of those terms. Then all I have to do is take care of the remaining terms. This is still negative AA. This is negative AA sine theta.
Shouldn't that be minus A2 though? Because...
This negative cancels with this one.
Over there, yeah.
I'm with you. This negative cancels with this one, so we get a positive A2 plus another A2 is 2A2, right? It's 2 times A2. I've got 2 of them.
No, but...
And when I move it to the other side, it's going to become negative.
I thought the one over there should be minus A2, right? Because if you look at the 0 equal negative A1 plus A2.
Ah.
Oh, plus, yeah. Yeah, you're right. Yeah.
Yeah, because all I did is I
Yeah.
took this
Yeah, yeah.
and I plugged it into, see, this is the mass balance, and I plugged the mass balance into the
Yeah.
momentum balance.
Yeah, I looked at that
Okay,
equation.
good, right, right. So this negative is not that positive. That positive is this positive. Good question. Anything else? All right. Well, what that means is A2, notice the negative signs will all cancel, right? Would be equal to, I can factor out an AA, I'd have 1 plus sine theta, and then divided by 2. Okay, so far? All right. Well, the last thing to do is evaluate it, because we know the area at A, we know the angle theta is 30 degrees, so we should be able to solve this. Let me check and make sure I haven't made a mistake here. I've got velocity for the mass, flow rate, velocity sine theta for, yeah, okay. Should be all right. So A2 is the area at A, which is 6.9827 times 10 to the negative third square feet. You have to multiply that by 1 plus sine 30 degrees over 2. So plug that in your calculator, please, and let's see how much area there is at section 2. So sine of 30, that's the one that's 50%, right? 0.5. So this is 1.5 over 2, which is 3 over 4, so 3/4 of this. So 75% of the area is over here. That tells you 1/4 of the area is over here. So what number do you have for me?
About 5.24 times 10 to the negative third.
Okay. We know it's going to be 10 to the negative third, right? So 75%, that looks reasonable. How about A1? A1 would be 25% of this, right? Because AA equals A1 plus A2. A2 is 75% of this. The other 25% would be right here.
You can just plug into the equation up there.
Yeah, plug it in here. You'll get the same thing. So what number do we get? Basically taking the difference between these two, what do you get for A1?
1.7.
That's good enough for us. 1.73 times 10 to the negative third square feet. And I shouldn't have put a box around this because that's really not our answer. The answer they were looking for is the flow rate Q. So now what do I need to do? Q1 is 80 feet per second, right? Because that's V multiplied by A1. And I should make this Q2 and put Q1 down here. So on this side, I need A2, which is right here, multiplied by 80 feet per second. So take this and multiply it by 80. What do you get? Or if you've still got this number in your calculator, just multiply it by 80 and I'll give you Q1. And that'll give you Q1. So 5.24 times 10 to the negative third times 80. And 1.73 times 10 to the negative third times 80 is how much?
For Q2, I got 0.419.
0.419 cubic feet per second. Okay, thank you. How about Q1? 0.139, thank you. Anybody second those two?
Yeah.
Pretty straightforward, it's just times 8. So there's Q1 and Q2. How did we get these two things? Well, we used conservation of mass. You know, the mass flow in must be equal to the sum of the mass flow out. And we use conservation momentum. Now, there were a couple of twists in this one. This is why I presented. The twists were that there were two exits. And so I had to account for the momentum of both exits, but some of the momentum was positive momentum. Other momentum was negative momentum. Notice that positive momentum coming in ends up being negative momentum in the equation. Let me show you what I mean. Oops. Get rid of this. The basic equation we're using is sum of forces equals mass flow times relative velocity entrance to exit. But notice that this mass times velocity, which is kind of like a momentum, but it's really mass flow rate, so it's not, but it's like it. This mass times velocity really would be a momentum. And all the exiting momentum, its sign just follows the coordinate system. So this is positive momentum coming out, there's negative momentum coming out, and so we leave it alone. But we have to flip the sign on the momentum. So notice that the momentum coming in at A, even though it was negative momentum, ended up giving us a positive contribution to force, which makes sense, right? Because if you want to get rid of the negative momentum, you have to apply positive force to do it. Okay? And notice that the x component, even though it was positive, when we sum momentum in the x direction, it gave us a negative contribution to the equation. So just be careful about that. I know that was a lot. Any questions? You don't even know what to ask. Are you going to put something like this on the final? No. Can you please not put something like this on the test?
The thing is, like, I understand if you, like, how you solve it step by step, but the problem is, like, on a test, like, how you come up with those steps, that's the thing.
The key is to work the homework. How do you come up with all this? You work the homework and you understand the homework. You don't just get through it. You don't just watch the video and just copy down mindlessly what I'm doing. I always liken this to a tour guide. I'm your tour guide. We're in the depths of the Amazon jungle, okay? When I'm with you, I've got the machete, I know the path, I chop the branches out of the way, you walk behind me and you go, oh yeah, okay, I could have chopped that branch. No, you couldn't have. Not until you build up your muscles, okay? Where you build up your muscles is on the homework.
Lifting weights.
Lifting homework, okay? So unless you work the homework and get to the point where you understand what's going on in the homework, you won't be able to solve the exam. But you can do this. Now, hints, what would I suggest? What I would suggest for succeeding in this class is that you find some friends to study with. If you have gotten to this point, most of you are in this class, you're probably either sophomores or juniors. If you've gotten to this point on your own, essentially, you've really spent more time on this than you should have. It will be very effective to get with some other people and study with them. Of course, you're also welcome to come to my office anytime you want. I want you to come to my office. I've kind of given up on asking students to come to my office because I guess you guys think I bite. I get a few people that will actually come and let me help them, and I love that because I like to help you guys. I like to see you learn. That's why I'm here. But I know, of course, it can be difficult to make time in your schedule, but I'm here pretty much all the day. The only time I'm not here is when I go pick up my daughter. Other than that, I'm here unless I'm in class. So see the office schedule on the blackboard or on my door. But one strategy for a study group is to find someone who is in the class that you know is better than you at this stuff. They don't necessarily have to have the highest exam scores, but they're the guy or girl that's capable of just getting it, right? They just understand it, they just write it down and do it. And then find someone else who's not as good at you as you are. Okay, someone that you can help, because it turns out when you have to explain the concepts to someone else, it clarifies them in your own mind, and it's very valuable. There's a couple guys over at the course I'm taking at U of L, and so far, they've asked me questions, and I'm thinking, I'm glad to help them. I'm a friendly person, I'm glad to help, but also I realize it's sharpening me at the same time. That's very valuable. Okay, so don't discount the value of working with other people. And don't discount the value of coming and asking me. I'd be glad to help you. Because I can give you more in person than I can on the video in terms of individualized help and really honing in on what it is you don't understand and helping you understand it. But you can do that yourself to some extent. As you're working through the homework, if you get stuck on something and you go and you look at the video and you go, oh, I see, write it down. Write down, I did not understand this because I thought X, Y, Z, okay? It's really this other way, okay? Writing that down is a good way of teaching yourself as if you were teaching someone else. I know it's a lot of work. I've tried to minimize the work by giving you these videos and eventually getting homework videos posted. I'm sorry I've been behind on that. That's what I would suggest. Okay? And then on the exam, just realize you're probably not going to get the right number, and that's okay. I don't grade these exams. I don't just look for a number at the end of every problem. I grade them based on your understanding of how to get the answer. That's what I grade them based on. So the more you can show me, that's why I want you to use symbols, because if you're using symbols, I can understand what you're doing. But as soon as you throw some numbers in there and start putting those numbers together, I'm lost. So the more you can show me that you understand, the more points I can give you. Okay? Even if it doesn't make sense, even if you get to the end and you go, you know what, I know I'm wrong, the best thing at that point is just move to the next problem and try to solve it. And then with whatever time you have left, come back and try to go through it again. Because you'll be surprised how your learning will be sharpened as you move through the problems. And you come back to the first one, you go, oh, I get it now. And you can finish it off or make corrections or whatever. Okay? Enough philosophy. Any other questions? All right, well, I guess I'll let you guys go. Have a good night.